तो देखो अब तक तो सब ठीक था, मेरी बच्ची का जो सगा लेना, मुझे नफरत है उस आदमी से, बहुत सीधी सी बात है। अच्छा मेरी बात सुनो, उस पे चलना चाहते स्मार्ट बाजार में
आज अभी आ जाऊंगा, चल चले
आप इसमें आज चलते
ना, बोले ना।
तो खाने में क्या बनाए?
मक्की की रोटी
बस सब्जी।
मम्मी दाल डोचरी बना लो।
दाल डोचरी
अभी तो पड़ी तेरे तो दाल डोचरी।
तो फिर मैं मुझे तो इडली खानी है, मेरे में मैं फ्राइडे
तेरे को दाल डोचरी पड़ी है,
तो उसमें तो डोचरी होगी ना, दाल
नहीं क्यों होगी, बिना देखे
ऐसे लास्ट वाली बच जाती है तो ऐसे होता है ना, पेट भर जाएगा उसमें पूरे खाने की है या कम है?
कम है
फिर
बाकी सलाद
नहीं,
यही होता है और क्या?
कोई नहीं होता।
तो कितने बजे का टाइम दे उसको?
आपके क्या बना रहे हो ये बताओ।
किसको देना टाइम?
जीवी को चलना है, वो तो उनकी गाड़ी से जाएंगे।
नहीं यूं नहीं कह रहा, जीवी को चलना है तो अपन।
हाँ बताओ
क्या खाना है आपको?
पहले एक चीज का क्लियर।
मक्की की रोटी दाल।
यार पापा फिर
तो क्या बनाएंगे?
तो सब आलू मटर की खिला देना मैंने।
पापा की पसंद की थी, मैं तो आलू मटर के पक्ष में होती ही नहीं हूँ कभी भी। मैं तो दाल, मेरे को तो सुबह दाल खानी थी, आपने बात की।
ठंडी अच्छी नहीं लगती इसलिए भी दाल बना देते हैं।
दाल फ्राई बनाओगी? फिर बना लो, फिर मैं उसको उसमें मिला के वैसे खा लूंगा।
रोटी खा लेना ना।
हाँ
ज्वार की
दाल फ्राई बना लो।
एक चीज हुई, चलो हाँ। तो कितने बजे चलेंगे अपन? 7:30?
हाँ।
या 8 बजे चले फिर खाना खा के ना? भाई जीवी का ही फोन आ रहा है कि बुआ कितने बजे चलेंगे, बुआ कितने बजे चलेंगे।
हमारे इन्फोसिस का
नहीं फिर साथ चल के आ जाएंगे, फिर आके खाना खा लेंगे हैं?
ਜਿਵੇਂ ਹਣੀ ਕੀ ਆਦਤ ਹੈ, ਹਣੀ ਕੀ ਕੁਝ ਵਜ੍ਹਾ ਚਾਹੇ ਜਮਾ ਨਹੀਂ ਚੱਲੀ ਗੱਡੀ, ਉਹ 5 ਸਾਲ ਦਾ ਰਹਿੰਦੇ ਕਿਉਂ ਉਹਨਾਂ ਨੇ ਜਿੰਨੀ ਉਹਦੀ ਕੈਸ਼ ਅਮਾਊਂਟ ਆ ਉਹ
Good evening, Ghanshyam sir. Am I audible?
Yes, you are audible. Good evening.
Sir,
Can you hear?
good. We are going
Can
to
you-
start within 5 minutes, so please wait for.
Can you hear me?
Yes, sir, you are properly audible.
Okay, we will start at 6 or 6:05.
Around 6. Yes.
So welcome participants. So today's session will be given by Professor Ghanshyam Singh, and he is the professor in the Department of Electronics and Communication Engineering, MNIT Jaipur. So I will explain you the brief research profile of Professor Ghanshyam Singh. And Professor received the BTech degree from NIT Silchar and MTech and PhD degree from MNIT Jaipur. He is the full professor in the Department of Electronics and Communication Engineering, MNIT Jaipur. He worked as visiting researcher, professor at University of Edinburgh, UK, University of Eastern Finland, and University of Japan. He has published over 200 research articles in the peer-reviewed journal conferences. He is the senior member of SPIE, IEEE, and fellow of Optical Society of India and IETE. He is the recipient of 2017 IEEE Distinguished Lecture Award for the Photonics Society. He has served as a secretary of IEEE Photonics Society, Rajasthan chapter Photonics 36. And he is presently serving as a vice chair of IEEE Photonics Society, Rajasthan chapter 36. He is the faculty advisor to Optica Society and IEEE Sensor student chapter of MNIT Jaipur, and as a member of SPIE Education and Outreach Committee. In the past, he had joined the research collaboration with researchers from University of Japan, University of Vienna, and a government university in Ukraine, Cairo University, Egypt. He is presently collaborating a multi-institutional research project with researchers from the University of South Africa and University of Science and Technology, China, Shanghai, and with Indian Institute of Technology, IIT Ropar. His current research interests include micro nanostructured photonics device for integrated photonics signal processing in optical circuits. So welcome Ghanshyam sir.
Thank you. Thank you.
So over to you, Dr. Lal Pratap. Please make the presenter.
Okay. Ghanshyam sir, now you are presenter. You can share your screen.
Okay. Thank you, Dr. Dhaka and Dr. Lal Pratap Verma ji. Can you hear me?
Yes, sir. You are properly audible.
Okay, my camera is it seems it's not working probably, but I can share my slides. Just wait.
Yes, sir. Yes, no problem.
Can you see the presentation?
Yes, sir.
Yes, sir.
Yes, it is visible.
Okay, fine.
Sir, make it full screen.
Wait. Can you see the full screen now?
Not yet, sir.
Can you see the full screen now?
No, it is in same mode right now.
But I've done the full screen.
So, sir, please first switch the mode in normal mode, editable mode, and then again try to.
Where?
No, it is not.
I can see.
So stop sharing and then share it again.
Okay, stop sharing is done.
Yes. Now please share it again. Then it might be work.
Okay. But why I'm not being able to see my slides on my slides? Because I can see only the names of the participants everywhere.
Now you can share your screen first.
Okay, okay. Can you see now?
Yes, sir. Slide is visual. Now switch the mode in presentation mode.
Slideshow.
Yes, sir.
Can you see now?
Not
Hello?
yet, sir. Not yet, sir. It is not in full mode, slideshow mode.
Because in my screen it is full screen now.
Full screen, okay. So when you are sharing the screen, so you are sharing individual tab or full window?
Only individual tab.
So if you will share the full complete window, then it might be work.
Okay, let me try again.
Okay.
Stop sharing. Share. Should I share entire screen?
Yes, sir.
No, but it will not share because I need to share the window only.
Okay, there is.
Can you guide me how to proceed?
So first, you need to switch your presentation in slideshow mode, and then utilize this. Then start sharing the specific tab.
Okay, wait. No, I'm getting the same thing.
Now your screen is visible, but it is not in slideshow mode.
So now if I'm making it as a normal mode, or so is this the normal mode?
Last one, sir. Last one is a slideshow mode. Last one.
I did it.
Last.
Now I did it the slideshow. Now I can see only my slides on entire screen, but I don't know whether it is.
But we are not able to. So can you share your slides? We will simply present.
Okay, I'll email this. You want to email?
Yes.
Okay, tell me your email ID.
lalpratap.verma.
Wait. Lalpratap.
.verma@jaipur.manipal.edu.
@Jaipur.
.manipal.edu.
Your spelling is LALPR. अच्छा आ गया.
Okay.
I'm sending it to you now.
Okay.
Check your mail.
Okay, sir. Just checking.
You got it?
Not yet, sir. Yes, received.
Guide.
Now, sir, is it available to you?
Yes, yes. Okay, fine. Okay, good evening, participants. I extend my thanks to the organizers of this ATAL FDP, which has been organized by Manipal University Jaipur campus. I congratulate all the people and the volunteers who are associated with this FDP for making it possible in the evening hours as well, so that the participation can be increased. And I'm also satisfied with this timing because it gives me better opportunity to discuss my topic amongst you. So today, as far as the FDP title is concerned, so my topic is also quite related with the uses of AI for development of integrated photonics. So in this presentation, I shall be discussing something about the integrated photonics, and then how the AI is going to make this technology more efficient, because the combination of AI and optical measurement technology can enables previously purely human know-how to be implemented in automated production processes. And it has already been established that with use of AI technologies, we can significantly improve the productivity, reliability, and quality of laser processes, which is a very important phenomena in integrated photonics. Not only this, AI can also support pre-selection of efficient optical systems design and development. Because when we talk about the integrated photonics, the two important part for development, design and development of integrated photonics is the material selection, as well as the selection of proper design structure. So there, in both the field, AI, that is artificial intelligence, and its related algorithms can support pre-selection of efficient optical system design and development. Because earlier, when we are not using AI, being a design and development engineer, I need to go through with lot of structures, with a lot of materials before I actually implement or realize my devices. But now AI can help us by pre-selecting the efficient optical system design and development. And it is not only me saying this, but it has already been established by many that AI can actually predict the optimization potential with up to 96% of accuracy. So that much of accuracy is, if it can provide, it can actually help us to come up with many more beautiful design in photonics technology as well. AI-based solutions may offer automated component optimizations that can check conventional design, and it may offers alternative versions as well. Like for an example, in laser processes, we sometimes need the bending and the cut sheet metal of processes as well. So that we can do at the click of a mouse, along with the cost benefit that can also be achieved if we are using some sort of AI algorithms for. Another example I can make, like AI can make laser-based manufacturing more intelligent than the what we have as on today. Similarly, there are few other examples like in additive processes, laser material processing, or we can say the automated design of optical systems. A well-trained AI can do in seconds what conventional algorithm used to take hours and days to calculate. So there also we can get help from the AI processes. Since this technology is developing rapidly, and it is already giving competitors who uses AI productivity advantage in terms of the integrated photonics as well. So that is how the AI is going to change the way we design and we develop the photonics products. So with this presentation, I will also would like to take your attention towards the what has already happened in the photonics field, optics and photonics fields, and what is new or what is latest going in, especially in the area of integrated photonics. So I'll go to the second page. Can you please move to my second page? Yeah. So before we discuss about the fundamental of integrated photonics, let me check what are the milestones the optical technologies have achieved so far. So way back from 1958, when the laser was first discovered, then within a few years, like mid of 60s, the guided wave optics was demonstrated in the lab, that how light signal can carry actually this information from one point to the other point, and that was demonstrated into the lab. And with the help of this invention, by the 1970, we started the producing low loss fibers. When I'm saying the low loss fibers, means the information which is to be carried by the light signal through the fiber should have the losses minimum. So that were also made possible that we started producing such fibers way back in 1970. And with the production of such fibers, it was made possible for us to think and lay down the long distance optical transmission. Similarly, in similar time, invention of semiconductor laser diodes also made possible optical transceivers more refined, highly refined. By in the between of somewhere in 70s and 80s, we started use of fiber in telephony. Initially, the networks which were based on fibers were called as synchronous optical networks, that is SONET. And the first country which started using the fibers for telephonic applications was the USA, where they laid down the fiber cable in Chicago way back in 1977, and they started using this technology. Can you come to the third page? By the mid of 80s, local area networks, metropolitan areas networks, these terms also came into the picture, where we started using the fibers which were based on broadcast and select architectures to pass on the information. Then in 1988, first transatlantic optical fiber cable was laid down, which is and there are two such cables going through that Atlantic Sea, and which are still we are using for our all sort of internet applications to communicate the data from one continent to the other continent. And similar fiber cables are being laid down between many other continents. By the late of 80s, we were able to develop the optical amplifier, which was termed as EDFA, erbium doped fiber amplifier. And then mid of 90s, the DWDM systems were explodes, where we started using the wavelength division multiplexing in dense media. So that's why this name is given, dense wavelength division multiplexing. By late of 90s, we started using intelligent optical networks. By 2000 onwards, the people started working with the triple O processing, where most of the devices were based on optical domain only. And that is why we are saying triple O, because all optical domain, where the input was also in the optical form, processing was also done in the optical form, and output was also received in the optical form. So that is why we are using these triple O processing words. 2000 onwards, people started, why not to replace some of the electronic components which we were still using with the communication networks, even with the fiber systems, with by the integrated photonic circuits. So in place of the electronic integrated circuits, we started thinking to replace some of the electronic circuits by photonic integrated circuits that can be more useful to become our networks more smart. Next, please. Next page. Yeah. So this table is very interesting. This gives an overview on the energy consumption per bit for a specific operation which we usually perform with our communication devices or the computing devices. Like the first entry, which says wireless data, the energy per bit requirement is 10 to 30 microjoules. Means whenever we communicate our data wirelessly, so this much of energy consumption is takes place per bit, that is 30 to 30 microjoules. Similarly, just to access the internet, the energy consumption is 40 to 80 nanojoules. Similarly, to provide various routing in an internet arena, we need to consume 20 nanojoules energy per bit. So there are all other operations mentioned in this table. If you just look onto this table, you'll find that if we go from top to bottom, the energy consumption are reducing. But the question is, when you see the operation which are written at the bottom side, like switching CMOS gate, energy in DRAM cells, floating point operations, communicating across chips, these are the operations which are actually performed onto a chip. And here the energy consumption is less, but the number of components onto a chips are actually too many. So that is why the total energy consumption becomes a problem for us. And that is why the most of the energy, according to this table, is actually used for communication, but not at the logic level. But even then, we need to think about to come up with the devices which will consume lesser energy as compared to the devices which are consuming electronic devices which are consuming as of now. Next page. Similarly, the companies which were providing the telecom applications for the people, they also started feeling pressure on their performance, and the three main reasons, because these reasons were published by the Cisco only in their uh, in a white paper release, where they mentioned that there was an extreme increase in network traffic in last 2 decades, where the growth rate was more than 30% per year. And because of to maintain that, to cope up with that much of network traffic, they need to place lot many other equipments, and therefore there was increased requirement of energy per cost, which was almost 10 times every decades. And because of that also, since they started using sophisticated and latest equipments, there were some ecological and economic issues as well with these companies. So what could be the alternate solution? The people started thinking about the alternate solution. One solution which was proposed way back 1 or 2 decades back, that can we integrate small photonic components onto a IC, so that we can replace some of the electronic ICs with the photonic ICs. So it was unnecessary to invent components for next generation networks as well. And the good thing is, if we start working with the integrated photonic ICs in place of the integrated electronic ICs, the benefit would be some of the benefit would be that we can have a high speed, high bandwidth, high capacity signal processing in the optical networks, immunity to noise. The network would be more secure and the cost effective as well. Next slide. Next slide. Also, the fibers are very much important for the interconnecting patterns, and these interconnecting patterns can be viewed in terms of the distance where the devices are having in between them. Like if we are talking about the local area networks, it has assumed that the devices are 100 meters apart from each other, so we need a fiber to connect them. Similarly, if we talk about the campus network, which is a part of wide area network, there the devices can be 1 kilometer distance apart from each other, and there also we can use the fiber. Similarly, within a country or within a single continent, the distance can be in thousands, 1,000 kilometers or 2,000 kilometers. So there also we can use the fibers to connect the devices. Similarly, we can also use the fiber for application where the devices are 10,000 kilometers apart from each other. Means we can provide the fiber connectivity between continent to continent. So this kind of interconnecting pattern is available all across the globe, where fiber can be used. Either we can use them for the lens application, for WANs application, even for to connect the devices within the continent, or to connect the devices in between the two continents, where the distance would be more than 10,000 kilometers. So at present, the optics is dominating for long distance connects. But similarly, if we talk about the chip connection onto a chip, so there the distance would be in either in the micrometer or maybe in the nanometer. So can we use the fiber fundamentals for interconnecting the devices which are placed onto a chips? Next, please. Next slide. Yeah. So what could be the problem with the interconnect if we are using them for? So what could be the interconnect problem if we are using them for a low distance for a short distance? Like short connections are more than the longer ones, because we are using lot many of ICs onto a network systems. So that's why there is a vastly greater amount of information to be communicated at shorter distance. So can we use the fiber concept or fiber fundamental in terms of the waveguides, and can we replace the copper wire which we are at present using onto a chip, or a communication between chip to chip where the distance is merely 1 to 50 centimeter. So as on today, the copper interconnects are more popular than the optical interconnects, where we use the waveguides to interconnect the chip to chip or device to device onto a single chip. Next, please. Next page. Yeah. So the next question is, why optical interconnects for short distance? Can we use optical interconnects for short distance? Yes, we can use. And if we are able to use optical interconnects or in the form of the optical waveguides for connecting the devices which are very, very closely placed, so we can able to reduce the energy consumption and we can increase the capacity also. So what could be the approach we can save the energy by eliminating the circuits and interconnection links. So quantum impedance conversions are also already into the top, where we can avoid the time multiplexing in short links by 10 to 100 femtojoules per bit total energy instead of 1 to 10 picojoules per bit. So here on this slide, you'll see there is a graph onto the right side. In this graph, the plots are being given for two important things: interconnection length and the on-chip power dissipation. So here you can see that there are two lines. One line is actually representing the electrical wires which have been used for connecting the devices for various distances. So here you can see the on-chip power dissipation is increases if the interconnection length is increases. But if instead of electrical wires, if we use optical fiber or optical waveguides or optical interconnects, you can see the power dissipation remains constant, even if no matter what is the interconnection length, whether it is 10 micrometer or whether it is 1 millimeter or whether it is 1 meter, the on-chip power dissipation would be the same. So with this graph, we can conclude that the optical interconnects would be good if the shorter distance is somewhere between 1 millimeter or beyond, because lesser than this, the power dissipation in electrical wires as on today is actually less as compared to the optical wires. Next. Next, please. So now, since we are talking about the integrated photonics, we need to compare it with the integrated electronics. So what are the basic differences? What are the similarity? We can talk about the integrated electronics and the integrated photonics. So way back in 1947, the first transistor was invented, which has been used to design integrated electronics, and within a span of 7-8 years, we came into the picture with the first electronic ICs, while the optical ICs were developed in the lab somewhere around 1969, for the very first times. And after the electronic ICs, which were came into the picture in 1954, we saw an exponential growth of EIC industry, that is electronic IC industry. And there are some operational and fabrication differences in between the integrated electronics and integrated photonics. So if we wanted to realize the integrated photonic circuit onto a chip, it is not every time possible to use the similar fabrication facilities which we are using the integrated electronics. So we need to develop some of the fabrication processes separately to come up with the integrated photonic devices. So more or less the PICs are equivalent to EICs, because in electronic ICs we use it is the electron which carries the information from one place to the other place, while in photonic ICs it will be the photons which will carry the information from one place to the other place. Now this the another graph is given over here, and this is basically based on the Moore's law, which says that after every 2 years the number of components which we are placing onto a chip would get doubled. That was actually defined for the integrated electronics. And you can see in over the last 40-50 years, the number of components or the elementary component, which is known to be the transistor, we are already placed billions of transistors onto a single chips. Like Intel SRM is the good example for this. But so we can see the slope of the integrated electronics is rising from 1970 to 2010. A similar slope is also being shown by the photonics. However, the number of components to be placed on the onto a chip are very limited to up to 1,000 only. But the good thing with this, what we can conclude with this graph, that the good thing is that both the technologies, whether it is about the integrated electronics or the integrated photonics, both are actually trying to follow the Moore's law till today. Next. Now, towards the integration of photonics, what could be the trend? So what we actually mean by the photonics, integrated photonics, it means that we'll have the important photonic components, whether it is the laser or whether it is the modulator or some passive components, some photodetector, the CMOS circuitry or filters, all together onto a chip. So this is an example. It's a beautiful example of electro-optic integrated photonics, because here we also have some CMOS circuitry which is electronic in nature. So we can place both the photonic devices as well as the electronic devices all together onto a single chip also. Next. And there are many good companies which are working in the direction of development of photonic ICs start from the Cobra, the Philips, the Siemens, the HHI, the Alcatel, the Entity, Lucent and Bell Labs, Metro, Infinera, and many important universities all across the globe are also investing a lot of money for their design and development of photonic integrated circuits. So this graph shows their developments from 1985 onwards till 2010. Next, please. And it is not only the initially the INP substrate was popular for to come up or to realize the integrated photonic devices, but it was not only the technology. It was earlier started using, people started using INP in most cases, but now onwards in 2010 onwards, the people have started using the silicon also. Silicon is already very famous in electron and integrated electronics application areas. So now the people have started silicon photonics also to come up with the integrated devices. Next. So the question is, when we are talking about the integrated electronics and integrated photonics, so we saw an exponential growth in integrated electronics, but it is not true with the integrated photonics. So what could be the reason why there was an initially slow progress in development of PICs? Because most of the issues were related with the fabrication issues, the economic issues, and there were some complexity also related issues with the photonic integrated circuit. However, the growth of PICs takes a greater speed when we invented the semiconductor-based LEDs and LEDs, and because of the invention of light-emitting diodes and laser diodes, we started coming up for the photonic devices, which were very good for the communication systems, the data storage and processing, and for sensing application as well. So far, many functional devices with use of a PIC application, we have a lot many devices which are already been in use for communication networks. Like we have amplifiers, we have attenuators, we have multiplexers, demultiplexers, modulators, couplers, switches, the lasers and detection devices, etc. The major breakthrough in development of PICs was when we invented the SOA and semiconductor laser. However, still there is a missing factor, that we still lack of standard fabrication facilities for integrated photonics and packaging technology as well. Next. The question is why the PICs are gaining popularity? Because they are proven to be the robust, more compact, and more flexible. We can integrate several components to make more devices than the optical fiber, and also the optical fiber can be used to carry signal from one PIC to other. So we, in place of the optical fiber, I'll use the word optical waveguides, where we can we can transfer these signals from one PICs to the other PICs as well. They have shown more reliability, and they have shown the satisfactory performance wherever we are using them. And they are also proven to be the energy efficient network systems. And it is expected, if we'll not go for from electronic to optical, but at least we may go for electro-optic network infrastructures, where our network would be having both the devices, like electronic devices as well as the optical devices, onto a single chip. So we may come up with the sort of devices which will have both technologies all together. So when we talk about the integrated photonics, so maybe we are talking about the planar light wave circuits, or maybe we are talking about the integrated optoelectronic devices, or we may be talking about the wafer scale technology on substrate. However, there are certain limitations with the technology as well. Next. So this slide is very interesting. This gives the a detailed history and evolution of monolithic indium phosphide based photonic integrated circuits developments. So initially from 1970, people started thinking about to come up with some devices which are suitable for photonic integrated circuits application. Initially, they started writing some technical papers on integrated optics. Then continuous wave semiconductor laser was discovered during the same time. And in between 1970 to 1985, there was a huge gap. No actual device was actually demonstrated in the lab, nor was available commercially. But from 1985 onwards, you can see lot many devices, including the INP based optoelectronic ICs, which uses the LEDs, laser diodes, and HBTs, then electromagnet modulator laser diodes, DBR laser diodes, Then 64 channel WDM selector, multi-section tunable lasers, channel monitors, 4 channel OXEs. The OXEs is the cross connects, the channel receivers, then transmitters. Then we got the 40 channel, 40 gigabits transmitters, 8x8 tunable optical router. So many devices were realized from 1985 onwards using the monolithic INP based PIC. So up to 2000 or 2005, this was the only material which was used most by most of the scientists or the engineer to come up with the PIC devices. Next. So if we define the technologies which are popular as on today to build up the photonic integrated circuits, so silicon photonics is now gaining more popularity than the INP. Then we have a silica on silicon or silica glass or the fused silica. Then we can have the members from third group of table integrated platforms, or we can use some of the polymers which are more suitable for photonic integrated circuits. So mainly the approaches are towards silicon and the member of third, fifth group of periodic tables. So we can use the material from that. So why the silicon? Because silicon is available. Its availability is a good point. The versatility, it also costs less, and it is more compatible with the present electronic fabrication technology. So we can use the present electronic fabrication technology for to come up with the silicon based photonic integrated photonic devices. While the good thing with this third group of semiconductors is that we can if we are using them, we can come up with the high power and high frequency application and high light emission efficiency, because laser application can also be possible. However, with the silicon, the laser application and the detectors are not possible. Next, please. Why this, and what are the good things with the silicon photonics? A track record of success is very good. They are more compatible with EIC fabrication technologies. Their performance, yield, robust, and they are more reproducible. We can produce the PICs in high volumes and more economically as well. Unique possibility of integrated electronic and optical function on the same chips. And they are also proven to be more transparent for the telecom windows. The telecom windows, which is 1330 or 1550, these at these telecom windows, the products which are based on the silicon platforms, they are more useful. And high packaging densities can also be provided by the silicon photonics, and that is why the silicon photonics these days is becoming gaining more popularity than the INP based photonic devices. Next. If we see the application area where we can use the silicon based integrated photonic circuits, so they are more useful for the data center application, more useful for the optical telecommunication processes, and also to build the interconnects where we can connect the devices onto a chip also. There is a possibility that we can reuse the huge technology base and supply chain from the electronic industry, because in electronics industry, the silicon material is widely used, so we can actually reuse the huge technology base. Similarly, many photonic components, whether it is modulators or the detectors or the sources, fully compatible with CMOS technologies also. However, still there are some challenges if we are working only with the silicon, because silicon has got indirect band gap, so laser source integration is very difficult, and they are poor absorber at 1550. So how to build the photonic photodiodes? So these two are bigger challenges connected with the silicon photonics. How also apart from this, attenuation is a problem. Interchannel interference can also be a problem, and polarization we need to avoid or control for long distance telecom applications. So these are the problems with the silicon photonics. Next, yeah, next. This I already covered. Next, yeah. Previously, back. Towards silicon laser, there are some approaches being proposed by various researchers. Like we can have a hybrid silicon PIC technology whereby we can bond the functional third, fifth group active components onto a silicon on insulator substrate, or we can have a bonding in between the third, fifth epitaxial layer by using the wafer or die bonding of third, fifth group of films on silicon and processing thereof. Or we can have a heteroepitaxial growth of third group on silicon by selectively growing the crystal on silicon substrate. And similarly, we can have a selective growth of germanium onto a silicon platform. so that we can also achieve some lasing operation onto a on a single on a silicon platform. Yeah, next. Next. Can you please update this slide? Yeah. Now, apart from the silicon photonics, there is another technology where we use the components, semiconductor components from third fifth group of table. That is known as third fifth semiconductor technology. If we are using the material from that group, there are some advantages which are associated with the members. Like we can get the solutions for lasers, the optical amplifier, the modulators and detectors. Monolithic integration for passive and active components within the fully functional chips are also possible. We can have a ultra high speed electro optic characteristics, and they are proven more reliable. When I talk about the reliability, that means we can use them for many more years as compared to the silicon photonic based components. However, certain disadvantages also associated with this type of technology, because they require extensive integration approach and also produces a higher propagation losses, and also there is a limit of mass production since the material are not available as frequently as compared to the silicon, and also they require little they have a low index contract, so it is difficult to operate with them. Next. There are certain applications for the devices which have been made with the third group semiconductor technology. So these applications are in the area of telecom, the datacom, the sensing, and the biomedical field as well. And also the another important area where these technologies can incorporate with the silicon-based platform, so we can have a hybrid integration, so that we can have some of the components which are made on the silicon platform, and some of the components which are made on the third group of semiconductor platforms. So we can have a kind of hybrid integration, so that we can have all the operation all together onto a chip, whether I'm talking about the lasers, the modulator, the demodulators, the detectors, everything can be on a single platform if we are using the hybrid integration of silicon and the third group semiconductor technology. Next, please. We can also make a comparison in between the integrated photonics devices which have been made by the INP platform, that is indium phosphide, or the silicon platform. So if you see this graph, you can see the blue dots are representing the various development of various devices which were made on INP platform, while the line and the dots which are in with the red colors, these are the devices which were developed by the silicon platform. So here you can see 1985 onwards, more and more devices were developed onto with the INP platform only. And from 2005 onwards, people started silicon platform to develop various photonic devices. However, the good thing is with this, that the slope of the development of silicon based products is actually higher than the slope of development of INP based products. So it is expected that by 2030 that the silicon photonics will be crossing the INP photonics devices, the number of devices which will be built with the INP base. So which will grow higher because higher level of integration first. There is a possibility the silicon will grow higher because the wafer size is larger, so we can place more and more component onto it. It is also economical driver which is integrating on silicon ICs, and we can use them for PCB, backplane, inter-rack application, data center application, and telecom application. And why is the slope is higher? Because we can have a better. If you see onto this graph, the slope is pretty higher than the indium phosphide based products. What could be the reason? Because we have a better process control, because this is already a mature technology. Silicon electronics, we are already working with that. So we can use the similar technology for developing the silicon based integrated photonic devices, because we can have a better process control. We can have more advanced process technology. More uniform materials can also be used for this. Next. Now we'll see some of the important major players and their achievements. Some companies like Infineon, DTN, the IBM, the Intel, they are all working together or separately as well to come up with many more integrated photonic devices. So Infinera DTN was the first company which produced the first commercial product based on the integrated photonics fundamental way back in 2005, where they have come up with a DWDM platform which was based on a 100 gigabit operating with 10 channels of intensity modulation of 10 gigabits per second with direct detection method. Also in 2011 and 2016, they have come up with 10 channel receiver PICs and also some products which they have named as Cloud Express 2 with infinite capacity engine where 100 gigabits Ethernet data center interconnects over multi terabits optical links, and it can deliver up to 1 terabits per second super channel in only one rack unit. So that was also possible, and we are actually, if you happen to be in the data center, you may see many more devices or item made by the Infinera company. Next. Intel is also not behind from this, because Intel is also investing a lot of money to come up with the integrated photonic based devices. In 2010, they have launched the photonic module with the high speed laser chips capable of moving the data at the rate of 50 gigabits per second by combining the silicon chips and the laser. And they have also started one big project which was given the name Night Mill Stages from 2010 to 2016. With the use of 45 nanometer technology, 22 nanometer technology, and 14 nanometer technology. And they created some of the silicon photonic based products by Intel developer forums only. And by the next, over the 10 years, they have also decided to use 10 nanometer Night Hill product with the Argonne National Laboratory to build the Aurora supercomputers. Similarly, the IBM is also competing with the Intel and the Infinera companies. In 2012, they had come up with the electronic photonic integrated chips, whereby they have placed the optical modulators and germanium-based photo detectors, which were capable to transfer the information at the rate of 25 gigabits per second and capable of shattering data around a terabits per second. In 2015, they have launched integrated wavelength multiplex silicon photonic chips as well, which support the electrical and optical circuits on the same chip package. Next. So I have taken the name of few companies only, but that doesn't mean that only few companies are working. If you see, if you wanted to see the complete list of companies, you can just Google the data onto the internet. You'll find many more companies, whether it's volume supplier, the Intel, the Cisco, the Infineon, Neo Photonics, Fujitsu, Leone, Silk, Renovis, or the Silo or the Juniper. So there are many more companies which are big giants which are actually working in the area of silicon photonics. Next. Now, being a researcher, you may be a little interested in what could be the next target if somebody wanted to work into the area of photonic integrated circuits. So there is a possibility that you can come up with the package where you can have a laser using the third group of semiconductors. Already IBM is working to that direction. Or we can have a target to get the laser, the waveguides, the photodiodes, and other optical gubbins right onto the processor die itself, alongside the copper wire and transistors. Again, the IBM is working in this direction. We may plan or we may think to deploy silicon photonic technology for switch-to-switch interconnectivity at the rate of 100 gigabits per second, and then to scale to even higher bandwidth, maybe up to 400 gigabits per second in the future. We may also design and develop PICs with use of fundamentals of plasmonics, the photonic crystal fibers, etc. And also there is some issues are also associated with the fabrication processes. So we can also take these challenges to trade off the power requirement, the cost, and the chip area coverage. So these are the possible areas where one can actually work upon if he or she wanted to work in photonic integrated circuits. Next. There are this table gives the material overview that which all the materials are popular and at what wavelength range the products are being developed. Like popular PIC materials are silicon, indium phosphide, silicon nitride, polymers. There are some glasses, silica, and lithium nitrates. And this table gives a comparison of these materials, whether we should design a device which are good for the long haul application or for the data center application, or for 5G wireless access network, or for automotive application, or for the or for the sensor application or for the medical applications, and also what are the typical wavelengths they can actually work upon. So these typical wavelengths are ranges from 700 or 400 nanometer to 1550 nanometers, and there you can see what are the material and what wavelength they can be work upon, and what kind of application they can be used. So this table is very interesting to get an idea that what are the different materials available to build the PICs. Next. So this is not the, if we see the situation in the global photonics, global area, that how the global photonics integrated circuit is estimated to reach by somewhere around 3,500 millions by 2024. When it started in 2016, people were using the hybrid integration or the monolithic integration or module integration. Similar trend is, or similar pattern is still going on. You can see in 2024, by the last year, there was an increase in the hybrid integration, and there was a decrease in the products which were made up of module integration. So more and more products are coming up with the hybrid integrated platform, either where we may use either the silicon or we may use the INP or some polymers. So more and more hybrid integrated solutions are coming up into the photonic integrated circuit market. Next. If we check the global photonic integrated circuit markets by component, which all components are being manufactured or realized using the photonic integrated circuit concepts, whether it is a laser, the multiplexer, demultiplexer, or a modulator, integrators, optical amplifier, and detectors, you can see the components classifications are given for two different years in 2016 and 2024. More or less the similar kind of developments is going on. The next. So this graph is also very interesting. This graph shows the area covered by the different material to build the photonic integrated circuits globally. So by raw material, so in what were the popular raw material in 2016 and what are the popular material in 2024. So here you can see different, more or less we are using the same thing: indium phosphide, silicon insulator, silicon, gallium arsenide, lithium niobate. So here you can see the area taken by the lithium niobate. More and more products are coming up with the lithium niobate and the silicon as well. Still the indium phosphide material is way ahead of many other components, but the silicon on insulator is also becoming a popular technology to build integrated photonic devices. Next. So this graph is very interesting. This gives the market revenue, that how the silicon photonics revenue will increase from 2019 to 2030. It is expected that it will cross 7,000 US million dollar business by 2030. So within this decade, there will be a huge increase in the revenue. Next. This also gives the market trend from 2013 to 2014. This graph shows the application of PICs in different sectors. So these sectors are the telecom or datacom or data centers or HPC. These HPCs are the high performance computing. So here you can see the more and more investment is now started. Initially, the photonic components were developed for telecom and datacom application only, but 2017 the some of the components were developed for high performance computing, and then 2018 onwards many more components were developed for the data center. If you see the bar chart for 2024 year, here you can see many mostly the components are targeting the data center application, then the components are targeting the high performance computing application, and then telecom and data application. Some other applications are also present here, which are related with the sensing and medical application. So more and more integrated photonic devices are coming into the picture to overcome to control these applications, to be suitable for these applications. Next, please. Again, this gives a different graph, product type or the application wise, how the transceiver active optical cables, the optical multiplexer, optical attenuators, and optical engines were developed during in 2019, and how much would be the percentage of these devices in 2017, 2027, 2027. So here you can see the comparison that more and more active optical cables would be developed by in next over the 2 or 3 years as compared to the 2019 arena. Similarly, the second graph shows the use of PIC's components for various applications like telecommunication, the military, the defense, aerospace, and others. So here you can see the more or less these products would be applicable in all the application areas. However, you can see there will be a jump that the more and more integrated photonic devices would be applicable for military purposes as well. So that is why the many countries are competing with either, whether you talk about the US or the China or the Russia or some of the European countries, they are trying to come up with many more products which based on the integrated photonic concepts. Next. These were the references which I used to make my slides. I've already shared my presentation with the organizers. So if you need this presentation for your further study, you can request them. So they will share my slides with you. And these are the references. If you wanted to get more detail about the integrated photonic concept, you can go through any of these references. Next. There are a few more other references mentioned over here. These are very, very important, although some of the references you'll find that they are quite old, 2013 or even 2005 also, because this integrated photonic concept was introduced way back in 19 and 21st century, starting of 21st century, but more and more products are started coming up from 2010 onwards only, where when we started using the silicon photonics as well in along with the INP technology. Next. So with this, I conclude my presentations. If you have any question, you're most welcome to ask. Thank you very much. Thank you. If you have any
Thank you so
question, you
much,
can
sir. Let's have an open discussion. If any participant have any query, then you people are most welcome. So thank you so very much, and the session was really very nice. So if you would like to share, meanwhile the participants ask any queries, if you want to share like your experience, your profile, and it is very overwhelming. So if you want to share anything from your side, the presentation, we all will appreciate.
You mean to say I need to share the experience from my side?
Yes, sure, because one participant has
Yeah.
but we would like to listen more from you.
Yeah, sure. Dr. Soumya, actually, I started working towards my PhD way back in 2006. So initially, I started working with some of the basic optical devices like optical switches, then optical couplers, the optical splitters. And by the end of 2011, I completed my PhD. But during my PhD, I got on a chance to visit the University of Eastern Finland. In 2010, I visited and I worked there for 6 months. And there only I got developed my interest into the integrated photonics, because I saw I had an experience to work with some of the nano fabrication facilities which were available with the University of Eastern Finland. And the good thing with that university is even I assume that most of the participants are from academic area only, and they are teachers with various colleges. So I would request if you visit their website, that is University of Eastern Finland, you'll find many of the facilities related with the integrated photonics, and you'll find lot much literature also is available if you wanted to read more about this. And the good thing is you can actually motivate your students to go for a master's degree in photonics only, and usually there is no tuition fees in Finland. You only need to take care of your living expenses. Uh, After coming from that university, I myself motivated around 3-4 students from MNIT, and they also joined MS courses with that university, and they completed their MS courses. And some of them now are industry, and some of them are some of them did PhD after that, and now settled with some good universities as a faculty member. So I would suggest you all, if you really wanted to do something good for. Okay, one question is there. I'll comment on it. Let me complete first me. So you can actually motivate your students to join some master's courses in University of Wisconsin. I'm not advocating that university only. There are many more universities in US as well, like University of Santa Barbara, University of California, which is in Santa Barbara. I happen to be there also. And because of my work in this direction, I got an IEEE Photonics DL Awards from IEEE Photonics Society in 2017 and 18. And utilizing that award, I visited many other universities where the people are actually working with many more devices which are suitable for integrated photonics. So if you really wanted to work, even if you are from the electronics background, you are equally eligible to jump into the integrated photonics area, because more or less the fabrication process are same for both the technologies. So you would only need to work upon the operating principle behind these devices, which is slightly different from the electronic devices principle. So that's from my side. I think there is one question somebody raised.
Yes, sir.
Can you just read that?
Actually, and
Uh-huh.
yes, sir, I am reading for you. The first question is from Mr. Nagar. The question is, how will the integration of photonics with electronics, that is electro-photonic integration, shape the future of communication and computing systems?
Okay, fine. So I have also opened this chat window. I'll go one by one. So let me first take the questions from Harshvardhani. She's asking, what are the simulation software used in photonics? So, madam, there are many software, although I'm not here to advocate their importance, but I can name few of them. Like OptiWave simulation tools are available to design various optical devices. Then we have a RSoft. Then we have few more devices like even MATLAB you can also use. The next is the question is how the photonics will use in wireless sensor network. See, you are talking about the wireless sensor network. So there are three things: wireless, the sensors, and the networks. So network will be based on the fiber links. So photonics is useful there in the network. Second thing is sensors. Many more photonic or optical sensors are already in use for sensing purposes. So we can use the photonics for developing the sensors with better efficiency and better quality. And even the wireless, as of now, this technology is related with the microwave technology only, but we can come up with the kind of uh, optics which is suitable for wireless application as well. So in both the time, in all the three terms, the photonics will make an useful contribution. The next question is from Mr. G. Nagarajan. He's asking, how will the integration of photonics with electronics, that is electrophotonic integration, shape the future of communication and computing system? See, we were already using the electronics component for our communication and computing systems. But if we are able to come up with the hybrid devices which are made up of electronic and photonic integrated platform, so it will shape the future in communication and computing system by two important ways. Number one is we'll have a more bandwidth available so that we can incorporate many more other applications. And number two, the speed of the operations. So if we are able to come up with the electro-photonic integrated devices, we can actually increase our computing systems speeds very fast. The next question is from G. Nagarajan, that what are the potential application of photonic neural networks in artificial intelligence? Yeah, good. So I would suggest you that there are some articles available which are having a title AI for photonics and photonics for AI. So both the technologies can actually help each other. The artificial intelligence can help the photonics technology. Similarly, the photonic technology can help the artificial intelligence as well. How? There is a very good architecture, or a blog is already available onto internet. I would request you to go through it. But AI can certainly help us by selecting the important or useful material, by selecting the useful structures to build up the or to realize the photonic devices. Similarly, there are many more photonic components, especially the quantum photonics. We can make more faster devices, which will make our AI and machine learning algorithms to run more faster on our devices. So that is how the AI can help the photonics, as well as photonics can help AI as well. So I hope I have already given all the answers to all the queries. Anyway, I'm just writing my email ID here onto a chat window. If you wish to connect with me, you are always welcome to write. This is my email ID, which I have just given onto the meeting chats, gsync.ec@mnit.ac.in. If you wanted to ask any questions, you can always send me your queries, and we can have
So,
further discussions. Yeah.
sir, do you have, you just mentioned a few universities so that our participants can explore the opportunities. Right now, as we all know that you are right now working in MNIT Jaipur. So are you open for also?
Can you please repeat the question? Are you open for what?
To take some PhD scholar as a guide. Do
Yes,
you
yes.
have vacancies so that any of the faculty or the
Yeah,
participant would like
there
to
are
connect?
3-4. Yes, yes. Okay, Dr. Soumya, I got your question. So there are 3-4 types of PhDs available in our department, and even with my groups also. One can do the PhD as a regular student, where the student will get a stipend or a scholarship of somewhere around 45,000 per month. Or you can do a PhD as a part-time student if you're working in some academic institutions, or if you're working in some industry, you can do your PhD as a part-time student also. In that case, you'll not be getting any scholarship, but you'll get the enough time to do your job in your academic institution and the PhD as well here in my institute. Then there is another PhD admission is possible, which is being supported by the government of India's another schemes. That is, and in that schemes you get another scholarship of similar type, like 45,000, and again that scholarship available for both the cases, regular as well as the part-time. Once you will complete your degree, you will get all the fees which you have deposited to the MNIT back according to that scheme. So you are always welcome to look upon our MNIT website, and probably the next admission will, the call for the next admission would be there somewhere in the April or mid of May. Just follow the guidelines, and you are welcome to apply for PhD positions.
So nice of you, sir, that you spared your time, and in fact you handled the questions from the participants, and even you replied my all questions so nicely. So thank you so very much that you spared your time, and we would like to listen more from you, hopefully in upcoming sessions. So thank you so very much, sir. And we will share the slides as you have already given the consent that the material can be shared. So we will share, but after taking the official confirmation as a consent from you.
Yeah, thank you very much. Thank you, Dr. Soumya. And thank you all
Okay,
the
sir.
participants for listening me patiently. And I wish you all the very best for this FDP. So we will be in touch with again in future. Thank you very much. Good evening.
Okay, sir. Have a very good evening, sir.
Thank you.
Bye-bye, sir.
Bye-bye.
So participants, we are done with our first session of this day. Very soon, our next speaker will be joining us. Meanwhile, you can drop your queries if you want to regarding the photonics and synthesizing or simulations. If you still have some queries, you can post here. I will collect all the chat messages and I'll post to the speaker. Otherwise, you still have email ID of Ghansham Singh sir. So you can directly post him the queries, but I will appreciate if you will send the queries in this chat box and the organizers will send this to the speaker. But you can also directly communicate with him. Speaker going to join us in next 3 minutes. So please stay glued.
Hey, hi, Dr. Somya. Are you able to hear me? Sanjay this side.
Yes, sir, I can hear you. And
Okay.
let me make you presenter
Yeah, no problem.
so that you can share your screen.
Yep.
How are you, sir?
I'm doing good. I'm doing good, right? So I was just in a meeting, right? So I just finished that and then I joined in.
Yeah, Dr. Arvind told me that you in some other
Mhm.
meeting, so
Yeah,
you will take a while.
sure.
So don't worry to listen to such a good speaker. The audience and I can wait.
Yep. Okay,
It's all
great.
fine.
Yeah.
So let me introduce. Otherwise, we have already had an introduction, but
Mhm.
let me have a short introduction, if you
Sure.
allow, sir, with the
Yeah,
participants.
sure. Please go ahead.
So,
So,
dear
is it going to
participants,
be, sir, yeah, sorry, is it going to be the same audience what we had yesterday? Or there can be people who have joined just today.
no, these are the same participants,
Okay,
sir.
great.
It's 6-day FDP. So
Mhm.
participants are same. So it's really nice that you have conducted one session and now you
Yeah.
can explore it further, or you can extend it to some other concept related concept.
Mhm.
It's totally
Right.
your
Yeah.
choice. And we have conducted the assessment
Yeah.
also
Yeah, sure. I will
for
share
the
the results of the
responses.
same. Yeah.
Yes, it's really nice that you can declare the results so that they can assess themselves.
Mhm.
So, dear participants, here the wait ends, and we do have Mr. Sanjay Kumar again with us. Let's welcome him. And we all know, but I would like to introduce him again, that he is the founder of Telco Learn Services, and he provides telecom 5G and 6G, cloud training, consulting services, 5G lab setup, and business development support to the product companies. So, without wasting any more time, we do have his contact details also. We can ask him further queries, and during the session, he makes the session so interactive. So let's start without any delay.
Okay. Let me share
So
my screen and then we'll get
yes,
started.
sir, you can. Yes, sir.
Okay. Let me know when you're able to see my screen.
Yes, sir. Your screen is visible.
And just to understand, it may take a couple of seconds to start that presentation. But do
Yes,
let
sir.
me know if you're able to see that in the full screen.
Yes, sir.
Okay. Great.
Yes, sir. It is full screen and it is clearly visible to us. So you can start the your lecture, sir.
Just give me a second. So let me stop the video for saving bandwidth for everyone, and
Sure,
we'll,
sure, sir.
okay, great. Okay, greetings everyone, and welcome to this session. In today's session, we are going to talk about AI/ML in 5G, 6G. As we all know that AI/ML is the buzzword today, and there are a few more things which are added to this buzz, right? The things related to Chat GPT, Llama 3, Bard, and things related to that, which is typically referred as generative AI. We will talk about the generative AI, LLM, and LLM is typically referred as large language models, and I'm sure most of you heard about it. And the latest things what we talk about in this world is we initially, last couple of months, there is a lot of discussion happening around AI agents. So you may not be able to see on the screen. That's fine. We will talk about it. Right? AI agents is the buzzword today. A lot of things, a lot of discussions happening around AI agents. And one of the latest thing which happened just last week is called as LTM. I'm sure some of you or most of you have heard about LLM. The LLM is typically the large language models. The large language models are the enablers for the generative AI. But now, what is this LTM? Are you aware about it? Do you know what is LTM? Can somebody help me to understand what actually is LTM? What is LTM? LLM, large language model. What is LTM? The LTM is large telecom models. Now, what we are trying to convey here is the telecom industry is not just any other IT industry. They have their own ways, they have their own data. So the traditional LLM may or may not be suitable for the telecom use cases. And to enable those use cases, we need some telecom specific data, telecom specific use cases, telecom specific case studies. And those are the things which are typically done with the LTM, which is large telecom model. It was a white paper which was recently introduced, and at the end of the session, I will be sharing the link of this particular white paper. And this is a must read for anybody who is working in the AI ML space or 5G 6G. Now, what we are going to talk about in this particular session is we will start with the evolution of wireless network. We'll quickly talk about what are the various things happening in the wireless network. And when we talk about it, we'll understand that we are not really talking from a network perspective. We are going to talk about from the perspective of AI ML, how AI ML has evolved over a period of time. Even though we have started talking about these things as buzzwords nowadays, but AI ML is not completely new to telecom world. It is happening from last 10, 15 years. How it is happening, what are the evolutions we have seen in the wireless network, and what are the use cases, what are the capabilities we may see in the upcoming networks of upcoming generation. That is what we are going to discuss in this particular part. We will also talk about overview to AI ML in 5G and beyond. We will talk about 5G network architecture overview with AI ML. Okay, so also we'll see how these network architecture are evolving with the artificial intelligence and machine learning. And then we will talk about key fundamentals of AI ML, generative AI, LLMs, etc. And at this point, we will also talk about LTMs, which are called as large telecom models. And I will also share a link where you can download the white paper related to LTM, right? And then we will talk about various 6G use cases and the research areas, the academia, the industry is working on, and then talking about role of AI in 6G network, challenges, and the future opportunities, right? So this is going to be the agenda for today's session, and I am hopeful that we may not be able to complete all these topics today, because originally I planned this as a 3-hour session, but now we are doing this 1.5 hour session today, 1.5 hour session tomorrow, right? So we may do, I have also built some labs, some kind of use cases related to telecom. So we will be doing some demonstration related to those use cases. So if we are not able to do it today, we will continue tomorrow, and then we will also do some kind of hands-on. I will also help you with some data sets if you may need, and then you can also try to deploy those labs, those training models, and then creating some predictions according to those models, right? And at any point of time, I've already shared my LinkedIn profile, and I will share it again today. So please feel free to reach out to me if you have any questions, any more support, any more details you need. I would be more than happy to support you in any of those scenarios. I'll not spend much time on my introduction. I've already done that, and Soumya has already shared these details today as well. And let us start talking about evolution of wireless network. Now, if we look at the telecommunication network started with 1G, evolved till 4G, and now we are talking about 5G and leading towards 6G. All these things, even though 3GPP or third generation partnership project came into existence when we started talking about 3G, but 3GPP is not only handling the third generation network, this is also creating the standards for 4G, 5G, and even 6G network. So initial release for 3GPP was release 99, R99, where we also refer this as R3 or release 3. We started with 4G in release 8, but release 8 is generally not called as 4G. We also call this as a 3G LTE, because we were not able to achieve the expectations of 4G. And release, excuse me, can you please mute yourself? Hello. Excuse me, can you please mute yourself? Mr. VB.
Dear participants, please mute your mic.
As an organizer, Ms. Soumya, can you please mute him?
Done, sir.
Okay. No, I don't think so. He's still.
Yeah, I think I disabled, but I
Okay.
could not.
No problem.
Okay,
That's
I have managed.
That's it.
Yes, sir.
That's okay. No problem. Right. So
Yes.
release 8 or release 10, that's where we started talking about LTE. And at this moment, network has started growing exponentially. Right. Now, what kind of challenges we bring in here? Right. So if you see, I'm not really talking about the data rates, the 2G, 3G, 4G, GPRS, WCDMA. What I'm talking about is the massive scale of the network which started growing when we started talking about 4G. Now, just to take an example, till 2G and 3G, there used to be, few 100,000 subscribers in every circle, every network. That has started growing to millions because everybody can get access to the internet, right? And the network has started growing exponentially, and that's where the management of these networks, doing it manually, became very hectic, right? Earlier, I was working with some network operation center. Whenever there is a fault in the network, we used to call the engineers, we used to tell them, go to the site, do the things, everything was happening manually. Doing this manual management was not possible in the next generation of network, in the 4G and beyond generation. That's where we started talking about lot of automation. Lot of it automation started coming into play. I can talk about these stories which happens in the network management because I request participants to be aware about that you are in a group meeting and where we already have 100 plus participants. If you keep on doing this session cannot go on. A humble request to everyone, can you please stay muted if you don't have any questions? We will have questions and answers at the end of the sessions.
And further, I would like to add, if you have any query, even then, please don't unmute yourself. It creates disturbance. You just raise your hand. We will address your query for sure. For sure. Please consider our request.
Right.
Thank you so much.
Yeah, thanks, Dr. Soumya. Thanks for your support. Right. So automation, a lot of automation has started coming into the market, right? So because we need to manage the massive amount of the network, massive number of base station, a hell lot of number of subscribers, and started, things started getting very crazy. And that's where we felt that, okay, manually managing all these things are not going to be possible. And that's where the automation started coming into play. And this automation is nothing but an initial introduction of AI ML in the telecommunication network. And we will talk about this further, what actually we need to manage in the network. And with the kind of 5G and beyond technologies we are talking about, these network cannot even sustain the kind of feature, the kind of functionality we are talking about. They cannot even exist if we don't have the greater support from artificial intelligence, machine learning, deep learning, orchestration, etc., as we will see in the later slides. So basically, evolution of the network, of course, we all know that when we talk about Shannon's theorem, we all know that, right? Capacity is directly proportional to the bandwidth. Right. So that is what we see when we have the data rates as 10 kbps, 20 kbps. Here the data bandwidths were around 200 kilohertz. Here we are talking about bandwidths of 400 megahertz. That is just from the capacity of the network. But how do we really manage these networks? How do we really enable more and more features? That is something which doesn't come from the bandwidth. That is come from the intervention of automation, AI, ML, orchestration, and a number of other things, which we are going to discuss further. Now, till 4G, from 1G to 4G, the intent behind these telecommunication network was just to connect human beings. The whole idea was to connect human beings. Starting with 5G, we are not restricting ourselves. We are not restricting ourselves only to the human beings. We want to connect everybody and everything. Let me give you perspective here. Why do we really need to talk about 5G? Let me take an example here. Today, the whole world population is somewhere around 8 billion, a little higher than 8 billion. We just crossed it a few months back. And we already have more than 8 billion mobile phones. So the kind of growth, the kind of have seen in last 15 years, we may not be able to see the same growth in next 10 years. So how do we really make money? How do the operators will make money? So they need to take this number from 8 billion to at least 30 or 40 billion devices. Now, all of us either have 1 or 2 SIM cards or 1 or 2 phones. Can we buy 5 more phones in future? Of course not. Now, from where this 40 billion number will come, that will not come from the human being, that will come from the devices. So connecting everybody and everything, that is going to be the key. That is going to be the key for the future growth of the mobile network operator. And that's 5G is not just one enabler. There can be a lot of other enablers, as we will discuss further, and they are going to pave the way how we look at the wireless network. So 5G has changed the perception. The way we will look at the wireless network is not only for selling the SIM card, giving more connectivity to the users. Right. Now, keeping this in mind, we have already divided our 5G network into multiple pieces called as EMBB, MMTC, and URLLC. Now, what I'm wanted to convey here is one thing I've already conveyed here, that the network, one physical network, is divided into multiple logical sections, where every logical section is called as one network slice. The interesting part here is, again, I'm not talking about network slicing here. I'm just referring to the discussion. But how do we really manage these slices? So life cycle management of these slices. How do we create these slices? How do we operate these slices? How do we maintain these slices? How do we allocate resources to these slices? That is something going to be very interesting, and that will be completely powered by AI ML. And without that, you cannot even imagine how do you allocate resources to the network slices. So complete network slicing mechanism, slice orchestration, everything has to be powered with the AI ML, artificial intelligence, and machine learning. Right. So creating these many slices, and this is going to go more intensive when we start talking about 6G network. Now, looking at this particular network architecture, we see that there are a lot of different network functions. There are a lot of different network functions, and unlike 4G, unlike 3G, these network functions are not the physical boxes. Traditionally, if you see, whenever I show a network diagram, and whenever I say show 4G architecture, 3G architecture, every time you see a box, you will assume that this is a piece of hardware with the integrated software. That every box what you see on the picture is actually a hardware, a piece of hardware with the integrated software. But that is not the case with the 5G. All the network boxes what you see here, they are all software applications running on a COTS hardware. If you're not aware what is COTS hardware, it is called as commercial off-the-shelf servers, which are typically some kind of general purpose processors, general purpose servers. So basically all the boxes what you see here, they are either some kind of VNFs, virtualized network functions, or they are some kind of CNFs, containerized network function. So virtualization and containerization. These are the two aspects, virtualization and containerization. These are the two aspects what we are traditionally using in the cloud infrastructure. And now we are extending those discussion to the a telecom network as well. Now, every network function what you see here is not really a single software application. It is a collection of microservices. Now, just to give an example here, till release 17, if we try to look at release 17, and the picture what you see here, even though it may look very complex, it is not the complete picture. If you look at till release 7, there are 28 network functions, which can cater to up to 102 microservices. So the boxes what you see here are not complete list. There are actually 28 network functions. Some of them are mandatory, some of them are optional, and they can provide up to 102 microservices. So the overall architecture is going to be very huge. The complete architecture is going to be very huge, and you may or may not implement. Now, how these network functions talk to each other, how these network functions communicate with each other, that is completely based on a protocol which is HTTP2. So we are moving away from traditional telecommunication protocols. We are moving away from traditional telecommunication protocols and getting into more generic, more standard protocols like HTTP. Like HTTP, where you are writing all the data, all the telecom specific data into the JSON format. Right. I normally deliver at least a 4-hour session just on this slide. When I talk about this slide completely, I talk about each and every network function, their functionality, their capability, how they communicate each and every service, the protocol logs. Right. So this is a pretty detailed discussion, but I'm just trying to cover this at a high level. Interestingly, all the interfaces what you see here, they are not actually the point-to-point interfaces. They are something called as SBI, or I can simply write they provide some kind of API endpoints. So these interfaces are basically the API endpoints, application programming interface, and this is also called as service-based interfaces, and that is why we call this architecture as service-based architecture. Now, this service-based architecture in the future, there are chances that it may be extended towards the base station as well. It may be extended to the UPF as well. That is not the case. As of now, these service-based interfaces are restricted to the control plane, and there are strong possibility that in the future, in the later releases, this service-based architecture may extend to UPF as well as GNodeB kind of network functions as well. Similar to this, even GNodeB, if we remember the discussion what we had yesterday, even this can be broken down into RU, DU, CU, radio unit, distributed unit, control unit, where even DU and CU kind of devices, they can be also created as a CNF or containerized network function. And this architecture, what we are using with the containerized network function is referred as a cloud native architecture. So cloud native is another thing what is very interesting, very integral part of the telecommunication discussion. And a little bit alteration to this, we also refer this as telco cloud. Telco cloud, right? So basically, this is something which companies are looking for. So when companies are coming for placements, coming for hiring in your colleges, they typically look for these buzzwords in the students, right? Which is sometimes missing in the colleges, right? So these are the things: cloud native, telco cloud, talking about containerization, talking about service-based architecture, APIs, etc., are pretty much important. And these things were completely alien to the telecom world, but now they have changed drastically and they become the main secret source of the telecommunication network. Now, I was already talking about slicing. So slicing uses the same underlying infrastructure. So our physical network remains the same, which includes the radio access network, transport network, and also the core network. Right. And on top of that, we are doing some kind of slice management and orchestration, which is completely powered with the power of AI ML. And at a later stage, agentic AI and Gen AI also become an integral part of it. And on top of that, we have the customer facing systems, which are nothing but some kind of OSS or BSS system, operation support system or business support system. Now, interestingly, there are some slices which are standardized and specified by 3GPP. Now, just to take an example, we have a value which is called as SNSSAI, which is a 32-bit value. Out of that, 8 bits are called as SST, 24 bits are called as ST, slice differentiator. If I look at SST, 8 bits, that means it can have values from 0 to 255. Out of that, 0 to 127 are the standard ones. The values from 128 to 255 are reserved for the custom slices. What is the meaning of the custom slice? What operator can do is, operator can create some kind of custom slices. 0 is given to EMBP. 0 is reserved, 0 is not used, 1 is given to EMBP, 2 is given to URLLC, 3 is given to MMTC, 4 is given to V2X, 5 is given to HMTC. All these things up to 127 are reserved for the standard slices. Standard slices means which are defined and designed by 3GPP. Beyond that, operators, mobile network operators can create their own slices. Mobile network operators can create their own slices and then, then sell those services, sell those slices to the retail customer, and these are called as NSAAS. NSAAS stands for Network Slicing as a Service. That means, in addition to selling my SIM cards, I can also sell these slices as a service to my retail customer. These, slices can be given to, metro rail, can be given to Indian Railways, some oil refineries, some mines, and number of different use cases which can be created for this particular offering. So even network slicing can be sold as a service and operators can generate some more revenues out of it. And the whole power, again, as I mentioned, this is not possible without the intervention of AI/ML. Even how to allocate the resources, how to distribute the resources among the slices, that can be completely powered by AI/ML algorithms. And maybe tomorrow we will see a demo. We will see that, hey, how do we really predict the resources given to a particular slice? So there can be one slice related to IoT, another slice related to AR/VR, another slice related to autonomous car or URLLC. How do we really allocate the resources to these particular slices? So we will see this with a demo using AI/ML. How do we really allocate these resources to the network slicing? Now, another interesting point for 5G, and again, this is not really restricted to 5G. Just give me a second. Let me get a sip of water. Sorry. Now, talking about something called as MEC. MEC stands for Multi-Access Edge Computing, and this is not really a new thing to the world. This is used in the cloud and IT infrastructure for many, many years and typically referred as CDN. CDN stands for Content Delivery Networks. Content Delivery Networks. Now, in the 4G, when we started implementing NB-IoT or EMTC, there was a challenge because many of these NB-IoT and EMTC use cases requires a lot of local processing. Now, to do the local processing, you have to build the applications closer to the end user. That means bringing the applications closer to the end user, to the edge of the network, to the network edge. And what is the network edge? Network edge is nothing but the base station. So what you need to do is you need to bring in some user plane functionality. And I'm assuming when I'm explaining this, I'm assuming that you already are aware about what is UPF, SMF, AMF, etc. So because that is something what I understood that already guys have the good understanding of the 5G network. So UPF is called as user plane function, which typically connects towards the data network or the applications. So now in this scenario, there can be multiple deployment scenarios according to the use cases. Some use cases, they require very, very quick response. And in that case, all these applications should be implemented or co-located with the base station itself. So whatever UPF, whatever applications you need, they are co-located with the base station. But when you deploy these UPFs and the applications to the base station, closer to the base station, this is going to increase your cost. This is going to give you the best performance, but at the same time, this is going to increase the cost as well. Now, to do a trade-off between the cost and the performance, we can also deploy UPF and the MEC on a transmission node, which is serving multiple base stations. This will bring down my cost a bit, but at the same time, performance will also go down. The performance will also go down. If you want to make it little more cheaper, little more economical, we can install it in a network aggregator. Even though you look at the same number of base station here maybe 3 to 4 base stations. Here there can be 10 to 20 base stations which are served by the same network aggregator, right? So in this case, your cost will further go down, but your performance will also be compromised. Last but not the least, just putting all these things in the central data center where you have all the other core network function. In this case, there will be no impact on the cost, but even the performance will be the least, right? So which one is good, which one is bad? I normally ask this question when I deliver these kind of trainings, especially the networking. I ask people, hey, do you know about TCP and UDP? People say, yes, we have heard about it. Which one is good? Which one is bad? People say TCP is good, UDP is bad. I say that's not the case, because it all depends on the use case what you have got, right? We consider that TCP is good because it is connectionless, it gives you acknowledgement and things related to that. But will that fit into every use case? The answer is no. Similarly, out of these deployment scenario, which one is good, which one is bad? That will strictly depend on your use cases, what type of use cases you have got. And based on those use cases, it will depend whether you go for this option, or this option, and this option. And interestingly, we need not to do the same for all the use cases. In the same network, one use case can have this kind of deployment, another use case have this kind of deployment. And this MEC also have something called as MEO. MEO stands for multi-access edge orchestrator, MEC orchestrator. That is typically another AI/ML engine which is talking about deploying the applications at the edge in the different location. So what I'm trying to convey here is that even MEC is not possible. MEC cannot be effective unless you bring in the power of artificial intelligence and machine learning in it. So there is something called as edge orchestration. And in some time, in maybe in the later stage, you may deploy some of the AI/ML algorithms at the edge itself. Because if you want to have federated learning, as we will discuss later, you need to distribute your intelligence. You need to distribute your training models, right? So that can happen where you can bring in all these things on the edge as well, right? So even this will require a lot of intervention from AI/ML. Now, this is the central point where we actually do the AI/ML, the network orchestration. Traditionally, if you see, we started with some kind of concept called as EMS. I'm sure many of you have heard about it, element management servers. Later, we started talking about NMS, network management servers. Then we talked about OMCs, operation and maintenance center, NOC, network operation center, GNOC, Global Network Operation Center. What they were actually doing is managing the network. What do we mean by that? We will discuss that in a while. Now, what we can do is there are multiple types of components in the network. There is a radio network, transport network, core network, a central network orchestrator. And if you see this here also, it says slice management and MANO. So just to add one point here, both MEC's framework, what we have discussed in the previous slide, and MANO framework, management and network orchestration, they both come from the same organization. And can somebody guess this organization? Who have created the specification for MEC and management and network orchestration? The answer is ETSI. So similar to the standards, when you look at related to wireless network, you look for the 3GP website. If you want to look at these standards from MEC perspective and MNO perspective, you have to refer to the ETSI website, where you will see all the details available as the standards and specification. Right. So at CMNO, and whenever we talk about network function virtualization or NFV, this framework comes from the at CMNO architecture only. Right. So basically, I have a central orchestrator. This central orchestrator is actually connecting to domain controllers or domain specific orchestration. We also refer these as DMs or domain managers. And then these domain manager will specifically manage their own networks or their own domains. So this is like creating a hierarchy in the network. Creating a hierarchy in the network where there is a central orchestrator, but he is not capable of, this is like a CEO of the network. And then he has multiple departments. And for every department, they have a manager. And these managers are managing their own departments. And this is how you make a effective company which can produce good results. And this is how we are doing the slice management and the network management in the telecommunication network. Now, I was referring to HCMNO reference architecture. Now, HCMNO reference architecture, without getting into too many details, they have the OSS/BSS systems which are connecting to the orchestrator. Orchestrator talks to the VNFM, which is typically managing the life cycles of the virtual network function. It also manages your VIM, Virtualization Infrastructure Manager, or VIMs, which is typically managing your network virtualization, network virtual function infrastructure, or NFVI, the NFV infrastructure, where you have the compute, storage, networks. All these things, what you see here, you can easily see these things in any cloud infrastructure. So the NFVI is nothing but the hardware software network hypervisor layer, and it can span across location for the DR, for the AG. DR is disaster recovery, AG is availability zones. VIM is managing the hardware resources. VNFM is managing the life cycle of the virtual network functions, and the orchestrator is managing all those things, and finally reporting to the OSS/BSS system. Now, this architecture, I'll not spend much time here because we have already talked about open, and here one interesting part here is these applications. So if you see the near RT-RIC and non-RT-RIC, we have already talked about this yesterday, where non-real-time RIC sits in the SMO, service management and orchestration. But near real-time RIC sits closer to the CU and DU, where it has multiple X apps. They have multiple X apps, and this have multiple R apps and X apps. So these X apps can be related to radio connection management, mobility management, QoS management, interference management, and the trained model which comes from the non-real-time RIC. In the non-real-time RIC, we have some kind of policies, configuration, etc., and they are typically defined and managed by some kind of RFs, right? So this is something where, okay, let me put it this way. Just give me a minute. Right. So let's see this. We will have a AI/ML model. First of all, we will need some kind of AI/ML model, but to train this model, we will need some kind of data, and data has to come from the network. Once the data is coming from the network, this data is fed to AI/ML model, and after this AI/ML model is trained, it is going from the non-real-time RIC to the near RT-RIC. So basically, near RT-RIC will get the trained model, and we will see the complete path at a later stage. So this trained model is actually, going to be provided to the near real-time RIC via the non-real-time RIC. Once this trained model is given to the near real-time RIC, near real-time is going to use this model to do various applications what they have here. So basically, all the near real-time control will be done with the AI/ML model, which is provided by the non-real-time RIC. Now, second. Okay, this is another interesting part where we talk about IMT 2030. IMT 2030, which is going to be our 6th generation network in release 21. And the release 21 timeline will be provided before June 26th. So before June 2026, the release 21 specification will be out. But as a bigger level, at a higher level, what are the usage scenario they're talking about? They're talking about one second. Just give me a second. Okay. Right. So there are 3 extensions to the existing use cases. Just give me a second. Somehow not able to use my ballpoint pen.
Excuse me, sir.
Yeah.
Sir, can you explain me about the handoff process that can perform in 5G, sir?
Sorry, handover?
Handover process, sir.
Okay, handover process. So
Yes, sir.
I think that's a very off topic, and in this discussion, it's very difficult to cover that, right? Because for that you need to understand the complete architecture, the call flows, and number of other things. I think this particular question may not be very relevant to the discussion that we are having here.
Okay, thank you, sir. Thank you.
Yeah. Somehow, let me just see what is wrong with my pointer. Give me a minute. Okay, right. So I think some issue with the PowerPoint. So we see here there are 3 use cases which come from 4G, and they are being extended to come from 5G. They are being extended to 6G as well. So EMBB becomes immersive communication. Some people they also call it as a XMBB, extreme mobile broadband. The URLLC, ultra reliable, is extended to hyper reliable. Instead of 1 millisecond, they are talking about 0.1 millisecond. MMTC, extended to massive communication, where they are talking about 10 million devices per square kilometer. However, there are 3 new verticals which are defined here. One is integrated AI and communication. So what we are looking at in 5G, the AI was coming as a cherry on the cake. It was more of a topping on the cake. But in case of 6G, we want this to be integrated within the network, and we also refer this as native AI. We also refer this as native AI. In addition to that, normally for sensing and communication, we use separate sensors, but in future, we are also going to have some possibilities which are called as integrated sensing and communication, right? So in the recent India Mobile Congress, which has happened in Delhi, there were some demos, there was some demonstration where the base station itself can can sense your location. So even these ISAC, so this is typically referred as ISAC, integrated sensing and communication. These can be integrated in the network itself, or ubiquitous connectivity or seamless connectivity across the network. So these are some of the usage scenario which are defined for IMT 2030, which is going to be 6G. This is coming from the ITU and 3GPP documentation. Now, let us talk about overview of AI ML in the 5G and beyond network. Now, what are the key areas of AI ML in telecom? And again, it depends on, to whom you ask. If you are asking from a network management perspective, the use cases can be entirely different. If you're asking a OSS BSS company, the use cases can be entirely different. If you're talking from the customer support perspective, the use cases can be entirely different. So there are a lot of different use cases, and then there are use cases even for the end user. So what we are trying to convey here is looking at who is the target audience. The use cases or the key area for AI ML are going to be entirely different. But just to understand at a high level, these use cases can be related to network management or can be related to network optimization. How do we really provide service assurance and a better user experience? How do we really provide predictive and data-driven insights for predictive maintenance, predictive, fraud detection and things related to that, and bringing new use cases for the end users and new revenue streams for the telecom operator. So basically, the whole idea of bringing in this AI ML is to generate some new revenue streams for the operators as well. Now, how it all started. Traditionally, if you look at it, and initially when we started talking about it, we started hearing about something called as TMN model. And I'm talking about this thing somewhere around 2000s, even before that. Telecommunication management network, which defines 5 layers: network element layer, element management layer, network management layer, service management layer, and business management layer. And you will see that these 5 layers have some or the other thing to do with these 5 parameters, what we are going to see in the next slide. Now, what is FCAPS? So I started my career with network management, and FCAPS was the keyword what was used during those time. But what is this FCAPS? Some people also write it as FSCAP. Instead of FCAPS, they write it as FSCAP as well, but one in the same thing. Now, what is FCAPS? The F stands for fault management. How do we really manage the fault of the network? C stands for configuration of the network. A stands for accounting. P stands for performance, and S stands for security. So in network, what you are going to manage? You want to manage the faults, you want to manage the configuration, accounting, performance, security, and traditionally they were all controlled manually. I still remember the day when there was a fault in the network. I used to call engineers and used to ask them to rush to the sites because I can't do anything from remote. Today also that is valid. There are many scenarios where there is a hardware failure, there is a connectivity failure. You can't do anything from remote. But as long as you can do something from remote, you can still do it, right? But even that option was not there in those days. So many of these things which were happening manually has moved to automation, has moved to orchestration over the period of time. And that is something which we are going to discuss in some follow-up slides as well. This TMN model, the TMN model, which had 5 layers, evolved into something called as TOM. TOM stands for Telecom Operations Map. TOM or Telecom Operations Map. And this TOM model later mapped to something called as ETOM model, what you see in this picture. So ETOM is just a subset of a bigger entity, which is called as NGOSS. NGOSS stands for Next Generation OSS, Next Generation OSS, which is a kind of combination of OSS and BSS, OSS plus BSS, which includes some kind of capability related to the network, some kind of capability related to the customers as well. Right. This itself is a discussion in itself. I'll not get into too many details related. So just to give an idea, TMN evolved into TOM, TOM evolved into ETOM, and ETOM is a subset of the NGOSS framework if you want to get into more details of it. Now, this is the first time where we started talking about doing F, C, and P with the automation. Out of these FCAPS, I have chosen three things: F, C, and P. F stands for fault management, where network can self-heal themselves. Where network can self-heal themselves, where I can maintain the failures, neighborhood localization, outages, power, etc. And then comes the C, where network can do the self-configuration. So network can self-learn about the network, subscribers, location, and they configure the cell coverage, estimation, cell deployment, authentication, system update, parameter adjustments, etc. And the next comes the P, where network can manage their performance by doing the self-optimization. They can monitor the mobility, signal quality, traffic, and according to that, they can do the optimization of quality, coverage, capacity, bandwidth, interface handoff, etc. Right. Now, each of these things, what you see here, can be deployed as a AI ML model. They can be deployed as an AI ML model. So we are doing this kind of training for some of the institutes and some of the institutes and the companies, where we are creating a 5 days program where we try to talk about each use cases and then try to deploy it by using AI ML model, train those models, test those models. That's what we are doing. However, this is not really a latest thing. This is a very old thing, which is there in the network from 2010s. And this is referred as SON. So SON was the early deployment of AI ML in the telecommunication network. Because if you see, self-learning is nothing but ML, machine learning. Even then, the machine learning, deep learning were not that popular. It is getting more intense over the period of time, right? So these SON network or self-organizing network are not new. They are at least 10 to 15 years old, but they are still valid. Even though when we talk about orchestration today, SON is going to be one of the subset of that, one of the use case in those bigger picture, right? So this is the starting point. As I mentioned, this is the starting point of the AI ML in the telecommunication network. This is the starting point of AI ML in the telecommunication network. Now, what is 5G and what is AI? 5G brings the extreme capacity and the multi-Gbps speeds. Right. So 5G we have already discussed. We have discussed enough. This comes with a capacity of say 20 Gbps at the peak data rate. They also provide you ultra high reliability, they low latency, providing you good security, support new and diverse devices, spectrums, deployments, etc. What is AI? AI gives you awareness to the context of the things what you are doing. Contextual awareness. Because of these awareness of the context, you can actually do the personalization. You can provide personal recommendation. When we watch Netflix, when we watch YouTube, we keep on getting some kind of recommendation. How that happens? That happens with the AI ML, because it gives you personalization at scale. And also creating intelligent, intuitive, and automated actions. And that happens because of self-learning. Because of self-learning. Of course, there is a lot of secret sauce goes into AI, but at a high level, this provides you contextual awareness and personalization at scale. But how these things are relevant to each other? Now, to make AI powerful, we need a lot of data, because to train the models, to build the insights, you need the data. 5G is generating the data. And when AI becomes better, it actually makes your technologies better, because these AI insights what you created, they can elevate the performance of the network. They can provide you more efficient resource utilization. They can also provide you energy reduction for longer battery life or a number of other things. So basically, what they are trying to do here is the advancement in AI is making 5G better, and proliferation of 5G is making AI better. So basically, they are the complementing technologies. They are supporting each other so that things can happen better for both of them. So 5G AI, and even when I say 5G here, it's not limited to 5G, 5G and beyond. They are going to make each other powerful. So betterment of AI will make 5G better. Betterment of 5G will make AI better. So these are the synergies what we are going to see in these two technology. Now, let us talk about how do we evolve with the 5G network architecture with the artificial intelligence and machine. Just give me a second. Let me get a sip of water and then we'll continue. Okay. Now, how 5G network architecture has evolved with the AI ML. Now, I'm sure I'm repeating this particular picture. We have already seen this. And as you remember, I mentioned this is not the complete picture. This is not the complete picture. This is just a part of it because there are 28 network functions, 102 services. But I'm not going to talk about all of them, but I'm going to talk about one interesting network functions. What you see here is called as NWDAF. NWDAF. NWDAF stands for Network Data Analytics Function. Network Data Analytics Function. So if you look at the name itself, it is related to data analytics of the network. So what is this NWDAF can do? What this NWDAF can do, it can work like a data analytics engine of the core network. Data analytics engine of the core network, and it can collect the data from all the network functions. So it can collect the data from SMF, AMF, PCF, UDM, NRF, AUSF, NSSF, etc. It can collect a lot of data here, run data analytics on top of it, and then provide these insights to PCF or the NSSF. So basically, this NWDF can create insights. It can create insights and then share those insights to the PCF so that the policies of the users can be modified according to the availability of the resources in the network, or to the NSSF, which can help the NSSF to optimize the slice usage. So basically, this NWDF is restricted to these two nodes, PCF and NSSF. And if you see the evolution, of R15, R16, R17, you will see that there are many new services are being added in the NWDF. So even though these NWDF things are pretty much naive at this stage, in future they may become very powerful. And if you look at the various releases, you will see lot of addition being done to the NWDF kind of network function. This is just one example we are taking in the core network. There may be more capabilities which are being built in the future. So NWDF becomes the data analytics engine for the 5G network. Now, without getting into too many details here, this is the ML model life cycle in the Open RAN. Right. We already talked about this at a high level. So we have some kind of ML designer, which will design the model. This model will be deployed to the, some kind of training host, where we have some kind of training model, which is getting the data from the data broker. After training this model, so we are just training this model here. And after training the model, this trained model will be uploaded to the designer again for the fine tuning. Once this is fine tuned, this AI/ML model will be published to the non-RT rig. And non-RT rig will set the policies and package models, etc. One second. Just give a second. Yeah. think something wrong again. Just need to minimize. Okay, so this is going to set the policies, package this model, and finally, this known RT-Rec will download this to near RT-Rec. So this model will be given to near RT-Rec, where we will be using this model for the near real-time control of the resources. After doing this, we will be generating more data. We'll be generating more data. This data will be collected. This data will be collected, and this out of this data which is collected, we will have create a common data lake, select the training data, and send this training data to the data broker. So basically, this is not a one-time activity. This will keep on happening. This will keep on happening, and this will be life cycle which is happening in the ML model life cycle for the OpenN. This itself is a completely detailed discussion. We'll not get into those details as of now, but completely powered with the AIML. This is something which we have already discussed about the network orchestration. Now, let us talk about 5G 6G network architecture overview with the AIML. Now, recently, there was a new alliance which was formed called as AI-RAN Alliance. Nowadays, it's really difficult to keep a track of the different alliances which are happening. Another alliance which was formed called a GTAA, Global Telco AI Alliance. Global Telco AI Alliance, which is created by some of the leading operators like Korea Telecom, ATAL, T-Mobile, etc. And they have come together to create the LLMs for the telecom network. Now, this AI-RAN Alliance talks about AI in the RAN, and they typically talk about three things actually. They have created 3 work groups: AI for RAN, AI on telecom, and AI and telecom. However, I have extended the same discussion to not just to the radio network, but to the whole telecom industry. And that can be called as AI for telecom, AI on telecom, and AI and telecom. Now, what are these things? Let us try to talk about these things one by one. AI for telecom. AI for telecom is talking about existing telecom applications. What are these applications? These applications can be network optimization, can be anomaly detection, can be resource allocation, resource management, predictive maintenance. How artificial intelligence can improve these processes, these applications, these procedures which are already there in the telecom. So you have n number of different things in the telecom. How artificial intelligence can make it better? That is referred as AI for telecom. However, AI on telecom talks about bringing new AI-driven applications which can directly run on the telecom infrastructure and generate new revenue streams. So basically, these are the new applications. Which are actually running on the telecom infrastructure, but giving new revenue streams for the operator. Both AI and telecom needs extensive resources. They need extensive infrastructure. And if we try to build 2 separate infrastructure, one for AI, one for telecom, that is not going to make sense. So what we need to do here is we need to create a procedure where sharing the underlying infrastructure and exploring the concurrent use of converged computer and communication infrastructure, both for telecom workloads as well as AI or Gen AI workloads. So basically what we are trying to do here is, we are we are trying to share the infrastructure where we are running our telecom infrastructure workloads as well as AI or Gen AI workloads. And that's what is referred as AI and telecom, right? So these are the three things what we need to keep in mind. And when telecom companies are working on it, they also need to understand that what are the areas they are targeting. And then only they can define the clear path in the things what they are doing. Now, who can be the participants of these telecom value chain? These participants can be network operators. The operators can actually improve their network automation by transforming legacy system. The participants can be telecom equipment manufacturers. These can be, developing AI solutions for the data centers and the equipments. Semiconductor companies to create AI-enabled chipsets. Software providers, where they are talking about integrating AI, ML, or deep learning algorithms for enabling automation in the telecom systems. System integrators, consulting companies, IT service provider, and last but not the least, the end consumer. So the overall AI value chain, what we are trying to create, these are some of the major participants. For that particular value chain. Now, without getting into too many details, if you see, this is how, just to take an example, how do we see migration towards the 6G core? Migration for the 6G core, where we relocate some of the network functions, we reuse some of the network functions, and we replace some of the network functions. So basically, these network functions like mobility management, session management, 6G RAN, etc., can be completely replaced. Some UDM and NRF kind of network functions can be reused, and user plane kind of functionality can be relocated to some other nodes. So these are some of the design concepts. It may or may not happen. As I mentioned, we are still 5 years away from the 6G standardization, which is expected to be in 2030. So these are all design ideas, design thoughts, which are coming from different groups. And this is just one depiction of that. Right. Now, before we start integrating these two things, let us also talk about key fundamentals of AI, ML, Gen AI, and LLMs. Now, artificial intelligence, machine learning, generative AI, and LLMs. Artificial intelligence, machine learning, generative AI, and LLMs. If you see the recent traction around Gen AI, and this AI ML is there in the network from many, many years. Right? It is happening from many, many years. The real traction happened when it is given to the hand of the common people. And that has happened with the introduction of ChatGPT. Now, if you see this, before ChatGPT, nobody has heard about Gen AI. Nobody has heard about generative AI, even though there were some tools available. I'll not say that this was the only one. Before that also there were some tools, but the real awareness was created when we started talking about ChatGPT, where they have all those tools were used by technical professionals and people like that. But ChatGPT has given this power to the common man. And that is where we have seen the latest traction. Now, what is this GPT? GPT, generative pre-trained transformer. So they are using some kind of transformer architecture to generate the content, which is powered by some kind of LLMs, large language models. In the upcoming discussion, we are going to talk about the fundamentals of AI, ML, generative AI, and LLMs, etc. Now, before we talk about it, I would like to pause for a couple of minutes and take up any questions. So any questions from anyone in the things what we have discussed till now, and then we can move on and start talking about AI, ML, Gen AI, etc. Any questions from anyone before we continue with the discussion? Please feel free to unmute yourself and ask those questions. Or maybe raise your hands and Dr. Soumya can unmute you. Any questions? Okay, if no questions, let's continue. Okay, now let us talk about what is AI, artificial intelligence. The intelligence which is typically considered as the human behavior. So humans are intelligent, as we call it. But what we are trying to do is, without explicitly programming the computers can program or can manage themselves, and they try to mimic the human behavior. They try to mimic the human behavior and do some kind of intelligent things, and that is typically referred as artificial intelligence. Now, what is artificial intelligence? It's a field of study that seeks to expand and emulate intelligent behavior in terms of computational processes. Right. Now, irony is just last week, my daughter, she's in 11th standard, and my son, who is in 5th standard, we were all studying the same topic as AI. Because today, even their books, even the books of 5th standard, they also have these topics in their syllabus, right? So my daughter, my son, all were studying artificial intelligence, right? So this is the time when we started our journey with the word star or MS-DOS. Our kids today, they are starting to learn these things even in their schools, even at the 5th grade. Now, this artificial intelligence, what it can do, where the machines can do things related to human minds, which are similar to learning and problem solving. Let us take an example. When a kid, starts walking, they typically, try to walk few steps, then fall down, then take help, take support from something, and then try to walk alongside with that thing. And slowly they try to learn, try to balance, and finally they are able to walk. Similarly, these things, machines will also fall. Machine will need lot of data points. Machines will need lot of data points to make these decisions, and the data is going to make them powerful. So these machines will be able to learn and solve the problems without explicitly programmed for that. That is what is artificial intelligence. However, this has a lot of different areas. We will talk about machine learning, NLP, expert system, and then a lot of speech to text, vision, computer vision, planning, robotics, lot of different major area of artificial intelligence. But let us talk about it. Let's talk about this at a high level. Now, artificial intelligence, what we have already discussed, where we are talking about ability of machines to imitate intelligent human behavior, what we have already discussed. A subset of AI, a subset of AI, which is called as machine learning. A subset of AI, which is called as machine learning. Machine learning is a system that learns and improves from the experience. So basically, we will be creating some kind of ML models, and these ML models will learn from a lot of data. What can be the data we are going to see in the next couple of slides, and help these machines to learn and build some insights, and these insights can be given to the artificial intelligence. But how these machines are built, these machines are built with some kind of DNNs, deep neural networks, and very complex algorithms. These are created with very deep neural networks and complex algorithms, and that is used to train models. There are a lot of different type of neural networks which are defined: RNN, CNN, GNN, etc. We'll not get into those details, but this is just at a high level. So a subset of artificial intelligence is machine learning. A subset of machine learning is deep learning. And within deep learning, there are complex algorithms and deep neural networks to train the models. Now, what are the different machine learning types? So initially, you may see 2 or 3 types like supervised and reinforcement learning. But over the period of time, there are a lot of new classifications being created. And if you look carefully, I have not talked about classification of the car or the house price, what you see in the traditional discussion. These machine learning classification, what we are talking about, are specifically targeted towards the telecommunication network. They are specifically targeted towards the telecommunication network. Now, supervised learning, without getting into too many details in the discussion around each type of machine learning, supervised learning can be used to do the network traffic classification, and it can also help you to predict the signal strength prediction. The unsupervised learning can help you to build the use cases related to network anomaly detection or maybe some kind of customer segmentation. This can be related to OSS systems. This can be related to the BSS system, operation support system and business support system. The semi-supervised learning can be used to do some kind of fraud detection in billing. Again, that is related to BSS, or optimizing the coverage of your network. The reinforcement learning can be used to enable your self-organizing network or doing the dynamic spectrum allocation. If you see in the wireless network, the biggest the biggest bottleneck is the spectrum. And now we have variety of different networks, 2G, 3G, 4G, 5G, and 6G is about to come, right, in next few years. So spectrum is always in scarcity. How do we really effectively manage our spectrums? That can be also powered by AI/ML. And if you know, we already have some concepts related to DSS. DSS called as dynamic spectrum sharing, not dynamic direct spectrum, but dynamic spectrum sharing, where the DSS allow you to share the spectrum with the 4G and the 5G technology, with the 5G and 4G technology. Now, the self-supervised learning can help you to do the 5G network health monitoring or maybe predicting some kind of traffic patterns in the network. Please note, this is not really the complete story. There can be 20, 30, 40 new other use cases related to telecom. These are some examples what we have taken for each of these different type of machine learning types. Now, moving our discussion to traditional AI and generative AI. Just to keep it very, very simple, traditional AI is more suitable to for the predictive analytics. The generative AI can do the automated content generation. So for example, traditional AI can detect the frauds and generative AI can generate the art. It can give you personalized recommendation. It can also generate the synthetic data. It can do the business process automation. It can create the automated content moderation, right? So these are some typical differences between the traditional AI and generative AI. Now, in addition to that, we have one more concept called as federated learning, which is also referred as collaborative learning. Now, let us take an example. Sorry, let us take an example. You have lot of different users and they have lot of different data. Now, these users cannot trust anyone with their own data. So if you ask me, hey, give me all your contact details or all your pictures, all the things what you're doing in your network, in your services, can you provide all this information to a server? I may not be okay with that. So in that case, what we can create is, we can create a 2-tier AI model. One is called as local AI model. Another one is global AI model. So every device will be running their own local AI model. And if you see, all these local AI models are different. They are specific to that type of user. And after using these AI models, they are going to create some insights and then share these insights with the global AI model, where global AI model is going to train its model by using the data by using the outputs of all these devices. In this case, both the devices and the central server is collaborating for the learning, and that is why we call it as a collaborative learning or the federated learning. Especially in the edge kind of use cases, when we talk about edge applications and things related to that, this collaborative learning are going to be very interesting, very important. Now, what is Gen AI and LLM? Generative AI and large language models. The generative AI, which is typically able to generate some kind of data which is not identical to the existing data. So this can generate new type of data which is not original data, and this data can be images, can be audio, can be video, can be text, can be n number of other things which are possible. Now, to do all these things, we need to have something called as LLMs, or large language models. Large language models, which is a general term that can be used to describe advanced natural language processing, or NLP task. So we are talking about NLP here, or natural language processing, which will be having some kind of open API GPTs, which are generative pre-trained transformer models, which can understand and generate human-like text on a larger scale. So this is what we have as generative AI and LLM, or large language models. But next is LTM. LTM is large telecom models. And this is going to be the last slide for our today's discussion, and then we'll open for question and answer. The large telecom models are the large-scale AI models similar to LLM, but they are specifically designed or adapted for the telecommunication industry. Right. I am going to share some of the one white paper which can be very useful for all these things. These models leverage advanced machine learning techniques, particularly large language models and domain-specific data to train these large language models. And what these can involve can be some telecom-specific training data, some kind of advanced capabilities and use cases, integrating them with the telecom ecosystem, doing the NLP for telecom, and creating the generative AI for telecom. Right. So this is all for today. What I'm going to do is I'm going to share two links. One is my my LinkedIn profile, as well as a white paper about LTM. Right. You can just go through it, and we will continue tomorrow. Tomorrow we'll continue with the session, and then after that we will be doing some kind of hands-on, where we will be deploying a model, training that model, and seeing some insight in that particular model. Right. So let me share those links, and then we will take the questions. So let me just. Is something wrong here? Let me on this file again. Okay. In a minute. Okay. Okay, I've just shared the link in the chat box. I've shared my LinkedIn profile as well as the link to the white paper. And let me look at the questions in the chat box, and then we will be, taking the questions if you have any. Let me start from the bottom. Please highlight some research area in 6G for academics. So Dr. Jayanti, we have that covered in tomorrow's sessions. We will be talking about some use cases, some research area which are open for the academics. There is another one, how generative AI leverages the low latency and high bandwidth of 5G network to enhance its capabilities. So, Dr. Jayanti, if you see, it's not about the low latency and the high bandwidth. Excuse me, if you have any questions, please ask it later or mute yourself. Right, so it's not about the low latency and high bandwidth, what matters to the AI. AI doesn't really care how fast you are ingesting the data. Of course, it matters over a period of time, but it is, crucial about the amount of data. The kind of data rates which are generated, the data which is generated with the 5G network, right? You will get more data to consume and create more insights. So it's not about the low latency and high bandwidth, it's about more data which you are feeding to these AI ML models. Just to take an example, if you see a few years back, maybe 5 years, 10 years back, the recommendation of YouTube, recommendation of Facebook was not that great because the data was not that huge. But today, if you see, the recommendations are, and take an example of e-commerce, Amazon, Flipkart. Nowadays, earlier you have to search something. You have to search something, then only it will show you the recommendation. Today, if you speak, then also they can give a recommendation. And even sometimes it happens, we don't even speak, we just think about something and then we see that thing on the e-commerce website, Flipkart or Amazon. That happens because there are other data points, other things what you've done, which may be related to this. Navinya, can you please mute yourself? Do you have any question? Okay, so we are doing a lot of other things which may be leading to this conclusion. So it's more about the data, less about the latencies and the high bandwidth. Right. There is another question. Okay. Some Abhijit says share PPTs of the session. Abhijit, I'm sorry, I don't share the presentation with anyone. Right. Please share the assessment link. The assessments will be tomorrow, not today, because this session was designed as a 3-hour session. What advancements are needed in optical beam tracking alignment for high speed OWs in the Nagarajan? I don't really work much on the optical side of it, so I can't really comment on this. So share your YouTube videos if you have for the detailed discussion for these. Yes, Dr. Jayanti, I have a YouTube channel. You can just search for Telco Learn or 5G on YouTube. Right, Telco Learn 5G, you will find my channel. I have a lot of videos. I keep on uploading a lot of videos on YouTube channel. Right, so there is something again related to presentation. So recording, I think the team will share. The presentation I will not be sharing. Okay, let me see if we have more questions. Please share applications of 16 EDM. Mr. Praveen, sometimes I may miss the abbreviations. Can you just elaborate what do you mean by EDM? Please suggest some simulation tool for 5G, 6G. Depends on what area you're looking for, Mr. Mani. There are at least, there are at least 100 ongoing projects related to 5G, which are all open source. You can build radio network, you can simulate the UE, you can simulate the core network, and you can find some of these videos which I've created on my YouTube channel as well. Educational data mining, I'm not very sure about it. I have not read or heard anything related to 6G use cases in education data mining. Right. Mr. Mohandas says, please comment on job opportunities in telecom sector. I think that may not be very much relevant to this discussion. Okay. So in addition to this, if we have any more questions, anybody would like to unmute themselves and ask those questions, please raise your hands and then maybe one by one, you can, try to ask those questions. Somebody says, please share your YouTube link. Let me see if I can do it now. Give me a minute. Okay, I can see that here. So I just shared the YouTube channel link in the chat box. Sorry, a second.
Greetings and a warm welcome.
Right.
Okay, so thank you, Sanjay sir.
Yeah.
On behalf of organizing team, I'm simply grateful to you to sparing a valuable time
Yep.
for our participant as well as for us. Now, Dhaka sir want to say something.
Yes, Mr. Arvind, please go ahead. Sorry, I was a little late because I was in another meeting. Sorry for that. Yeah, let's continue.
Okay. It's okay, Sanjay ji. It's okay. So, Sanjay ji, thank
Yeah,
you for
thank you.
sharing your invaluable expertise with us today. Your insights were truly enlightening. So, thank you so much.
Yeah. Thanks a lot. Yeah. So we will continue with the same discussion tomorrow at 7:30, and we will also do some hands-on related to AI/ML with telecom.
Yes, sir. Thank you, sir.
Okay, sir.
Thank you very
Thank you.
much.
Thank
Have a
you
good
very
night.
much.
Take care. Thanks a lot.
Good night.
Okay,
Thank you,
bye-bye.
everyone. Take
Good
care.
night.
Yeah.
Thank you, everyone.